In this video, we're going to take a look at even more tests for convergence of infinite series. So in the previous section, we really introduced three of them. We looked at the integral test, we looked at the comparison test, and then the limit comparison test. So we're going to introduce some more here. And this first one centers on the special case when the series we're looking at is alternating. So it alternates between positive and negative terms. All right, so when you see the notation b sub n versus a sub n, we're going to use b sub n to denote, when we're looking at an alternating series, the absolute value of the terms. All right, so if I was looking at this series here, then the idea would be that a sub n are the actual terms that I'm working with, whereas b sub n would be me ignoring the thing that's generating the negatives. So b sub n would just be the 1 over n part. Okay. The alternating series test, what it says is if you have an alternating series, right? So negative 1 to the n minus 1, and by the way, it could be negative 1 to the n. That part isn't what matters. All that matters is that you have a part here that's generating positives and negatives alternating. And then you've got some other part of your formula that is always positive. Then you have to just check these two conditions to make sure that your alternating series is convergent. Number one, that b sub n plus 1 is less than or equal to b sub n. Okay, what does that really mean? Then each term in the sequence is smaller than the one that came before it. That's all that means. And then if in addition to that, the terms of the sequence converge to 0, then you will always have convergence for an alternating series. And this picture illustrates nicely why this makes sense. So notice each time the length of the line gets shorter and shorter, right? So you know that if this line eventually goes to 0 and it's just going back and forth, eventually it's going to settle on a particular sum right here in the middle. So this example that I have up here is convergent. Right? It's definitely convergent because we just checked those two things, right? Is it true that 1 over n plus 1 is always less than or equal to 1 over n? Of course that's true, right? The next one in the sequence always yields a smaller value than the one that came before it. And then, of course, the limit as n goes to infinity of 1 over n equals 0. So with that, I just checked condition 1 and condition 2. They were both met, so I know that this thing is convergent. And remember that if we took away the alternating part, right? If we took away the alternating part, I'm running out of space to write, but if I did this without the negative 1 to the n, remember that's divergent. Right? So sticking that alternating action in this series took it from a divergent series to a convergent one. All right, so this one's asking us to determine whether this series is convergent. So again, we're just going to check those two conditions that we just learned about. So first of all, b sub n, what is that? That is me ignoring this part, the negative 1 to the n. So b sub n is 1 over the square root of n plus 1. All right. But then we also need to look at the one that comes next. So that would be 1 over the square root of, and so instead of plugging n in, I'm plugging n plus 1 in where n was. So of course that's 1 over the square root of n plus 2. So condition number 1 says that we need to look at b sub n plus 1 and ask, is that less than or equal to b sub n? Right? Is that true? Well, sure it is in this case. If you're adding more in the denominator of this fraction, that's going to produce a smaller number overall than if you had less in the denominator of the fraction. So condition number 1 checks out. And then is it true that the limit as n goes to infinity of b sub n equals 0? Well, that's the limit as n goes to infinity of 1 over the square root of n plus 1. And of course, if you let n go to infinity, you're going to get 1 over a really big number, so the limit is 0. So that condition checks out, and so that means with those two conditions, our series is convergent. All right, so another example here. We have an alternating series, and it wants us to determine whether this series is convergent. So, right, 1 for any term in the sequence is the one that came before it, always bigger. And number 2, do the terms approach 0? Sorry, let me erase that. All right, so now you can see in this one, what are we looking at here? We're looking at b sub n, right, is exactly what you see. But then b sub n plus 1 is going to have n plus 1 plugged into both of these. All right, now this one's a little bit more complicated than our last problem. There's no question that in this problem up here, when you add more to the denominator, this term is smaller than the one that came before it. But this one's a little more complicated because we're adding 1 to both the numerator and denominator. So that's a little more complicated of a situation to try to sort out. So what's sometimes a good idea is to check condition 2 first, right? Because if condition 2 doesn't check out, then we don't need to even worry about whether this is bigger or that's bigger, right? It won't even matter. So let's take a look at number 2 first. So we're going to take the limit as n goes to infinity of n squared minus 1 over n squared plus 3. And remember, our technique when we see stuff like this is to take a look at the highest power on the bottom and say, let's multiply by 1 over that power on both top and bottom. And so we're going to really be taking the limit here of, on top, 1 minus 1 over n squared, and on the bottom, 1 plus 3 over n squared. So both of these terms are heading to 0 as n gets big, so we're left with just 1 over 1. So the limit is 1. Well, that is not what condition 2 is telling me needs to happen if it's convergent. So this is actually nice. I don't even have to do the analysis in number 1. Number 2 failed, so therefore we know that the series is divergent. All right, so one more example here. So it says determine whether this series is convergent. So again, let's think about our two conditions. This the b sub n plus 1 term always needs to be smaller than the term that came before it. And we also need the limit of the terms to be 0. All right, so let's see, which one should we attack first? In the last problem, remember we took note, right, that it's kind of a complicated situation to try to decide when you're adding on both top and bottom. Right? Adding 1 on both top and bottom, which one's bigger? Now here's what I'm thinking. The natural log is a very slow growing function. And so I'm thinking that adding 1 to the bottom is going to kind of carry more weight than adding 1 to the top. So I'm pretty sure that this is a smaller number than this. Okay, but we'll readdress that if the limit is 0, right? So might as well check to see if this is even an analysis we have to do first. So starting with condition 2, we want the limit as n goes to infinity of the natural log of n over n. Now let's think about what the numerator and denominator are doing here, right? As n goes to infinity, like we said, the natural log, it's a slow growing function, but it is a growing function nonetheless, right? That's what the natural log graph looks like. So as n goes to infinity, this will go to infinity, right? And of course, this one goes to infinity. So whenever we have infinity over infinity, what should we be thinking? That's right, L'Hopital's rule, right? So we'll go ahead and say this is going to be equal to the limit as n goes to infinity of the derivative of the top divided by the derivative of the bottom. And so this is the limit as n goes to infinity of 1 over n is the derivative of the natural log of n. And then the derivative of n, of course, is just 1. So here's a case where we definitely do see the limit equaling 0. Okay, so condition 2, it checks out. All right, so now we do have to check on condition 1, right? So remember, I said that I suspect that whenever you add 1 inside a logarithm on top and then add 1 in the denominator, that basically adding 1 in the denominator has more effect, and so overall this fraction should get smaller. Okay, but that's not exactly a proof. So what I want us to remember here is that we do have the power to think of things in terms of functions. All right, so I'm going to do this. I'm going to consider the function natural log of x over x. And we've done this before where we said, you know, essentially when I say that I want the next term in the series to be smaller than the one that came before, I'm asking for the series to be always the terms of the series to be always decreasing, right? I'm asking for a decreasing sequence. And when we were looking at sequences, what we did was we said, you know what, sometimes it might be good to look at a function of the formula and then see when that is decreasing. And we know we do that by taking a derivative. So I'm going to go ahead and calculate f prime of x. Okay. And so remember, if you don't want to use the quotient rule, you can pull this up as x to the negative 1 and use the product rule. I'm just going to go ahead and use the quotient rule here. So I'm going to take the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom function squared. So that equals 1 minus the natural log of x divided by x squared. All right, and so we know that f, right, is decreasing when f prime is smaller than 0. So let's try to figure out, when is it that f prime is smaller than 0? Well, the bottom doesn't matter, right? X squared is always positive. So what matters is when the top is less than 0. Okay? But when is the top less than 0? The top is less than 0 when the natural log of x is greater than 1. So let's remember, what is x when the natural log equals 1? Okay, well, remember the natural log is the log base e, so the natural log of e equals 1. So this is going to be true when x is greater than e, right? And remember that e is between 2 and 3, right? So what we can do, so we'll say, 2 point whatever, right? So in other words, what we can say is, because if x is greater than e makes our function decreasing, then what we can say is that the terms are decreasing for, and for what, right? Well, for n greater than or equal to 3, right? So what we see is that, okay, yes, in fact, this property does hold here, right? For all n greater than or equal to 3. So that means condition number 1 checks out. And so the series converges. All right. Thinking back to the last section here, one thing I want us to recall is that with the integral test, we had a remainder theorem, which said that if you take a series and you add up so that you get a partial sum, right? So adding up a certain number of terms, we were able, with the integral test, to come up with an estimate for what that what the remainder is, what the error is in using the partial sum as a guess of the true sum. So the alternating series estimation theorem gives us the same thing for alternating series. All right, so the remainder, or the absolute value of the remainder, right? Because you might have to add it or subtract it depending upon whether that partial sum sums to something positive or negative, is always going to be less than or equal to the term after you ended your partial sum. All right, and that makes sense. Let's go way back to our picture here. All right, so in our picture, let's just, for example, say that I wanted to do the partial sum, S5, right? So that would be adding these up. Okay, so that would land you right here. Well, you know that the sixth one is going to take you past where the true sum is, and and dip down below it in this picture. And so the actual remainder, right, at this point is the distance between the actual sum and S5. So you know that this error involved here has to be less than the term B6. All right, so here's how we can use this. Example 4 says approximate the sum of this series to within 1/1000th. So all I do is I start adding terms, but as I go, I keep track of how big of each term is. Okay, now of course, 1/1000th, right, is 0.001. So I'm going to start adding. I'm going to say 1 over, and so I'm starting at n equals 0, right? So let me be real careful about it. 2 times 0 plus 1 to the third. So there's my first one, plus -1 to the 1, 2 times 1 plus 1 to the third, -1 squared, 2 times 2 plus 1 to the third, okay? And I'm probably going to have to keep going, but let's kind of see where we're at as we go. So this is going to be -1 to the 0 is 1, and then on bottom that's 1 cubed, which is 1. All right, plus, well, -1 to the first is going to be negative, so this is going to be minus 1 over, and then 2 times 1 plus 1 is 3. 3 to the third is 27. Plus, -1 squared is 1, and then 5 to the third is 125. Now, as I'm going along here, I'm going to approximate what these are. Well, I would say 1/1000th, that's 0.001, but it's also 1 over 1,000. Okay, so as long as I have something smaller than 1,000 down here, I know that I haven't reached the point where I would stop yet because I want to get within 1/1000th. Okay, and if you wanted to, you could also, actually approximate the sizes of these. So this is 0.037 right here, right? 1 over 125, 0.008. So you can see these are not below 0.001 yet. All right, so minus 1. So the next one's going to be -1 to the third over 2 times 3 plus 1 to the third. So that's going to be -1 over 7 to the third power. So 7 to the third power is 343, which gives me 0.003. Okay, so still not below 0.001. So then let's go ahead and say our next one is -1 to the fourth over 2 times 4 plus 1 cubed. So that's plus 1 over 9 to the third power, right? So 9 to the third power is 729, which is approximately 0.0014, we'll call it 0.0014. Still, this is bigger than 0.001. So we'll go again. So this would be 11 to the third power. So this is going to be minus 1 over, okay, 11 to the third is 1,331. That is below 1/1000th. So that's 0.00075. Okay, so what does this remainder theorem say? The remainder, when you have the partial sum of up to n terms is always smaller than or equal to the next term that you don't include. So if I make this term here the one that I don't include, then the sum of the terms that came before it, the remainder for that partial sum, the remainder for this partial sum here, has to be less than or equal to this number. So now I've guaranteed that I'm going to be within 1/1000th because this number is smaller than 1/1000th. So I take just those first 5 terms there, and then I add those up, and that adds up to 0.969. So that's going to be pretty darn close to the right answer. Okay. So just to make real clear what we're saying here, the remainder of this, which is what? The 0 term up to the 4 term, right? So R4 is going to be the absolute value of that is going to be less than or equal to 0.00075, which is less than or equal to 0.001, which is exactly what they asked us for. So this is our answer with confidence that it has the degree of accuracy that was requested. All right, now we've been talking about alternating series, right? Plus, minus, plus, minus. Another question that we might need to answer about alternating series is, kind of, is it only the fact that it's alternating that's allowing it to be convergent, or would it have been convergent even if it wasn't alternating? Okay, so what am I talking about here? So again, let me go back to our favorite examples here. So remember this series versus this series, right? We know that this one's divergent, right? And we know that this one's convergent. So clearly it's the -1 to the n, it's the alternating behavior that allows this one to be convergent. The 1 over n in and of itself, without that alternating, would have been divergent, right, as we know. So one of the things we might want to ask is a series absolutely convergent? So a series is absolutely convergent if literally the sum of the absolute values of all the terms is convergent. All right. So, and here's a theorem to follow up with that. It says if a series is absolutely convergent, then it is convergent. Then that just means like, all right, so if you can take the absolute values of all the terms and add them and get a finite number, then if you didn't have the absolute values, of course it's still convergent. Okay. So example 5 asks us to determine whether this alternating series is convergent. All right, and then determine if it is absolutely convergent. All right, so let's just do convergence. It's an alternating series, so let's do the alternating series test. So number 1, look at b sub n plus 1, right? Is it less than or equal to b sub n? And number 2, right? The limit as n goes to infinity of b sub n is supposed to equal 0. Okay, so here what we have is b sub n plus 1 is equal to e to the negative n plus 1. And be careful about your parentheses here, right? This is saying take the negative of whatever's in the exponent, and we want to put n plus 1 in the exponent. And then b sub n is, of course, e to the negative n. All right? But, of course, this is equal to 1 over e to the n plus 1. And this is equal to 1 over e to the n. Okay, so working on part 1 here. So we know that it is, in fact, true that if you're adding more to a positive exponent, In the denominator, that's going to give you a smaller number than if you're adding less to a positive number in the exponent in that denominator. So that checks out. And then number 2, right? If I take the limit as n goes to infinity of e to the negative n, that's going to be the limit as n goes to infinity of 1 over e to the n, and I know that that is also 0. So that means it is convergent. Okay, but is it absolutely convergent, right? So if I put absolute values around every single term, well, we can get rid of these absolute values by understanding that e to the negative n is always a positive number, right? So it's the negative 1 to the n that sometimes produces negatives. So let's just get rid of the negative 1. So this is just asking, right, is this a convergent series? Now, what I want you to do here is to think about what we've learned before. Okay, think about what we've learned before for a moment before you let the video play on longer. Can you tell me if that's a convergent series right off the top of your head? At first, it might not be super easy to recognize, but I could rewrite this as e to the negative 1 raised to the n, right? And e to the negative 1 raised to the n could become 1 over e to the n. But the thing about 1 over e is that is a number that's smaller than 1, right? So if I take 1 over e and plug that in my calculator, I get 0.368. So I get a number smaller than 1 in here, but what is this, right? This thing is a geometric series with r less than 1, right? So remember, a geometric series looks like this: n equals 1 to infinity, a r to the n minus 1. Never mind that I'm starting at n. That can be fixed by just moving, a constant around. That's not a big deal. This is a geometric series. So this here is convergent since it is a geometric series with r less than 1. And so therefore, our series is also absolutely convergent. All right? Both convergent and absolutely convergent. In other words, you didn't need the alternating nature in order to make this convergent. Without it, it would have been convergent anyway. Convergent to something else, by the way, right? It doesn't mean they're would go to the same number, but they're both convergent. Oops. All right, so the final test that we're going to introduce in this section is called the ratio test. And the ratio test is one that we're actually probably going to use the most out of any of the tests you've learned. So here's what it's saying. It's there's a lot to it. What it's saying is it needs you to take the limit of ratios of consecutive terms in the series. Okay, that's what it's asking you to do. So here, I think it may be necessary for me to really make sure we're clear on what this notation means. So let's say for a second that we are looking at this, right? So this is our series. So a sub n is our series, or are the terms of our series. So when we're talking about a sub n plus 1 over a sub n, that would be, in this case, 1 over n plus 1 divided by 1 over n. And they want us to take the limit of this, okay? So the reason that they want us to do that is they want to get us to be able to get a sense for how the next term in the series compares to the one that came before it in terms of absolute value. So the claim here is that if you can say that this ratio converges to something that's less than 1, then it turns out that the series that these came from is absolutely convergent. Okay? At first that might seem kind of random, but here's what it's saying. The only way that this ratio can end up less than 1 is if not only do the next terms in the series get smaller than the ones that came previous, right? Because this has got to be smaller than that in order to have a limit that becomes smaller than 1. But not only that, but it's got to be getting small fast. Okay? It's got to be getting small fast. And the reason that it has to be getting small fast is, let's take a look at this one here. This number is definitely smaller than this one. But when I simplify it, I get this. But we also know that something like n over n plus 1, right? This will go to 1 as n goes to infinity. So in order to get a limit that's smaller than 1, you're going to have this thing going to getting small much faster. Or another way of saying it, it has to be going to 0. It's got to be going to 0 quickly enough that this limit can settle down to something smaller than 1. So it's in cases like that you're going to get convergence. If you end up with something bigger than 1, then obviously that means that your terms aren't even necessarily they're going to be growing overall, right? That means the top is bigger than the bottom, right? So that's definitely not what you want for a convergent series. So if it's greater than 1 in the limit, or if it just doesn't exist, then you have a divergent series. And then if it's 1, we're not sure. So here's an example of when it would be 1, right? If you take the limit of this, you would get 1. And the ratio test would say we don't know. We know this one that I was using happens to be divergent, but the ratio test wouldn't be able to tell us that because this is the inconclusive situation. All right, so this one asks us if this particular series converges. So we do have an alternating series, and it introduces this idea of a factorial. So in case you don't have much experience with factorials, just here's a quick tutorial on it. So if I say 5 factorial, or 5 with the exclamation point, that means 5 times 4 times 3 times 2 times 1. That's what 5 factorial means. And kind of a strange aside here is that 0 factorial actually is equal to 1. So that's how we define 0 factorial. I know that's kind of strange, but you actually are allowed to have a 0 factorial, and that's what you get. Okay, so with that, does this series converge? Well, we have a tool at our disposal here, right? We have this ratio test. So let's see if we can apply it. Right, so the ratio test tells me that I want to take the limit of the absolute values of a sub n plus 1 over a sub n. All right, so what does that mean in this problem? that's going to mean we're going to take negative 1 to the n plus 1, n plus 1 factorial divided by 1,000 to the n plus 1. That all is just a sub n plus 1. We are then going to divide that by negative 1 to the n factorial over 1,000 to the n. And the thing about the ratio test is it makes a big mess at first, and then we keep our fingers crossed that it kind of settles down after we do some work. And this one will. So first of all, when we have a fraction divided by a fraction, we know that we can take the bottom and multiply by the reciprocal. I can also get rid of the negatives, right? We have absolute value bars here. So because we have absolute value bars, this negative 1 up here and this negative 1 down here don't make a lick of difference. And then the factorial and the 1,000 raised to powers, those are both positive anyway. So at this point, I can zap the negative 1s and just focus on these other terms and then, or all these other factors, and then just drop the absolute value symbols. So there's my top. And then I'm going to multiply by the flip of the bottom. So this is 1,000 to the n over n factorial. Now remember, we're trying to get a sense of if this limit exists. Does it go to 1? Does it go to something less than 1 or something greater than 1? All right, so when I'm looking at doing some simplification here, we're probably a lot more comfortable noticing the simplification that can happen here. We have 1,000 to the n plus 1. So in the bottom of this first fraction, I am definitely allowed to call this 1,000 to the n times 1,000 to the 1, right? Multiplying like bases means I add the exponents, and so I'm just applying that rule in reverse. And that's really nice because the 1,000 to the n completely goes away. All right, so that's good. Now how about the factorial? So over on the side here, let's kind of work this out. So if I have n plus 1 factorial, that means I'm taking n plus 1 times n minus 1, and I just keep multiplying until I get down to, 1, right? Just like when I had 5 factorial, I start with 5 and then just multiply on down. Okay, but what is this right here? If you take n times n minus 1 times all the way down times 2 times 1, that is just n factorial. So what you can always do is if you have something like n plus 1 factorial, you can write it as n plus 1 times n factorial. And so that comes in really handy here, because that allows the whole factorial thing to just go away. So those cancel out. All right, so I am left here after all that simplification with the limit as n goes to infinity of n plus 1 over 1,000. And if you let n go to infinity, then of course this goes to infinity, and so the limit does not exist. And so what the ratio test tells me is that whenever the limit is greater than 1 or it's an infinite limit, does not exist, then we know the series is divergent. So the series is divergent by the ratio test. All right. So let's take a look at another example. All right. So apply the ratio test to this series. So we'll be taking the limit as n goes to infinity of, all right, so it's going to be a sub n plus 1 over a sub n absolute values. So this is the limit as n goes to infinity of n plus 1 to the negative 2 divided by n to the negative 2. All right, there's no negatives in here at all, right? You're not going to get a negative number on the bottom or a negative number on top. So I can drop the absolute values. And then also I can, send this up and this down so that the exponents become positive. So this will become the limit as n goes to infinity of n squared over n plus 1 squared. All right, and now there's a couple of ways that you could go from here. If you want to expand this out, be my guest. It's not bad, you just FOIL it, right? But I'm going to do this problem a little bit differently so that even if this number was something big like a 5, you would still be able to use my same technique, right? Because if there were 5s in the exponent, we wouldn't really want to expand all this out, right? So what I can certainly do is, instead of bothering to expand it out, I could say this is n over n plus 1 to the second power, right? We're allowed to take and distribute the square to the top and bottom of the fraction. And then within there, I can see that the limit, and you might even just look at it and notice the limit's got to be 1. And if that wasn't jumping out to you right at first, remember your strategy is to multiply by 1 over n on top and bottom. And then I can see easily that what's happening here is that as you let n go to infinity, this goes to 0. So your answer is just 1 over 1 squared, which is 1. All right, so what does that mean? Going back to our ratio test, that means that it's equal to 1. So that means it's inconclusive. We don't know. Now, in this particular example, we do know. Okay, we know that this series here can also be written this way. So let's write this. The ratio test is inconclusive, but we do know it converges because it is a p-series with p greater than 1, right? P equals 2 in this case. So by a different test, one we already learned, we know that it converges, but just note that, hey, the ratio test was inconclusive. So that if that ever happens to you, just, shrug your shoulders and say, well, the ratio test didn't help there. Let's look for another way to determine whether it's convergent or divergent. All right, last example. This one asks us, does the series n to the third over 3 to the n squared converge? Okay. So let's take a look here. I want to try the ratio test. So plugging in n plus 1, plugging in n, what does that look like? So we've got n plus 1 to the third divided by 3, and be careful here, n plus 1 squared, right? So I'm taking n plus 1 and squaring it in the exponent. And then down here, n to the third, and then 3n squared. Now there's not any negatives to be seen here, right? So I do not have to keep bothering with these absolute values. And I can definitely take this bottom fraction and multiply by its reciprocal. All right, and so our goal here is to try and get some stuff to cancel. But I know that I can't get stuff to cancel unless things are being multiplied, right? So right now, like for example, I see 3 to the n squared here, and I see 3 to the n squared involved in this, but unless that is multiplied by everything else on the bottom of this fraction, I can't cross it out. So because I know this is in there, I'm going to try to make it appear. So I'm going to go ahead and expand out that n plus 1. So this will be 3 to the n squared plus 2n plus 1, right? So I'm just foiling stuff out here to get that, right? Okay. Well, that like we said, we need multiplication, right? But anytime you have addition in the exponent, we can make it into multiplication. So this can be 3 to the n squared times 3 to the 2n plus 1, right? That's the same as adding those exponents all with the same base. So we've at least gotten part way to making this a lot simpler to look at. We can get those 3 to the n squares canceling out. All right, but we still have a lot going on here. So let's see if we can make some sense of it. We had kind of a similar situation earlier when we had an n plus 1 to a power and an n to a power. And so this isn't, like I said, the only way of addressing this, but I kind of like it because it keeps things simple and doesn't force me to multiply stuff out. So at this point, I can certainly kind of rearrange my fractions a bit. So I'm going to just, this is a 1 left over here, so I'm just going to kind of let this guy hop over with the n cubed. And so I'm going to have 1 over 3 to the 2n plus 1 times n plus 1 cubed over n cubed. And then just like the trick we did in, I think it was the previous problem, it's okay to say this is n plus 1 over n to the third power, right? As long as that power is the same, we can be doing that. And then even better, I can say that in here, this is n over n, which would be 1 plus 1 over n to the third. So let's think about what happens here as n gets really, really big. as n gets really big, this guy goes to 0, and this guy goes to 0. So we have this part overall going to 1, this part going to 0. So if that's what happens, then that means that the limit is equal to 0. And the ratio test says, and it doesn't have to be 0, remember, with the ratio test. It just means it has to be less than 1. So if the limit of this ratio is less than 1, then we say that it is convergent by the ratio test. Now before I end here, that was our last example for this section, but before I end, I want to go back to something that I should have discussed with this particular example. So this one diverged, right? What I want us to understand is the power of this factorial, because this is probably pretty new to us. This factorial, the fact that we're getting a divergent test, you might be wondering, like, what is the factorial like compared to the exponential? Because we know exponential grows really fast. So I just want you to realize how basically big a factorial is. The fact that you can have 1,000 to the n, right? An exponential with a base of 1,000 here, and that is still not growing fast enough to make this series convergent when you have a factorial up here. So I just wanted to point that out, since a factorial is kind of a new thing to us.